We left our last video with the idea that contraction actually started with the release of calcium from the sarcoplasmic reticulum. And I mentioned that for a muscle to relax and to be able to be pulled back out, something on the other side has to contract and pull it out. But the reabsorption of calcium into the SR is key for allowing that to occur. So this brings about the idea of what happens after you die. So you're all probably familiar with the general idea of rigor mortis. And that is that when you die, the sarcoplasmic reticulum tends to leak calcium. It's a relatively leaky structure. So without active reabsorption processes going on, calcium is going to pour out. So when you die, no more nerve signaling telling the SR to reabsorb. That means the calcium leaks out and it triggers a muscle contraction, just as if a nerve had come along and told the SR to release calcium. In this case, there's no signal coming to tell the SR to reabsorb the calcium, so as long as there was ATP present, so energy available, calcium released, you get muscle contraction. And for the first several hours after death, there is energy still available in the cells, and so this means that muscles start to contract after you die. This results in a dead person stiffening. So if you've ever heard of dead people being referred to as stiffs, they're literally talking about their muscles contracting and their body becomes very rigid and inflexible. At some point, though, rigor mortis will resolve. And this has to do completely with environmental conditions during this time frame. Typically within an hour or a couple of hours after death, the stiffening, the contracting of the muscles becomes obvious body-wide. Typically within, let's say, 36 to 48 hours after death, you would expect rigor mortis to be resolving or completely resolved, again depending on environmental conditions. The warmer it is, the faster this will happen. The cooler it is, the longer it will take for this to occur. So what's really happening when those muscles become uncontracted at this point is not that calcium was reabsorbed. It's not that the thick and thin filaments let go of each other, but it's that at that point the muscle decomposed enough that it literally fell apart. So it was rotten enough that it fell apart, could not maintain that contracted status, and the body then becomes flexible again. So onset of rigor mortis is release of SRs, calcium, triggering muscle contraction. Resolution of SR, or resolution of rigor mortis, is decomposition of muscles and the thick and thin filaments rotting and falling apart. Delightful stuff to consider, I know. Each muscle cell or muscle fiber has its own nerve that tells it what to do. So that means if you have hundreds of thousands, perhaps millions of muscle cells, you have millions of nerves involved in telling them to contract or to uncontract. The time frame in which a muscle contracts and then starts to relax is typically pretty short. So in the top image here we have a generic isometric twitch, and we'll get to isometric and isotonic contractions later on. But right now we're going to say this generic muscle contraction starts at time 0, and there's going to be a latent period for a couple of milliseconds. Let's say 5 milliseconds here, in which the signal has been received from the nerve, but we don't have any contraction yet. So that tells us that's about the time it takes to generate that action potential, send that signal down to the T-tubule, and release the calcium into the functional unit of the muscle. So a 5-second delay in getting from the nerve to the point where calcium is released and the thick and thin filaments start pulling on each other. From about 5 milliseconds on out, for perhaps a number of milliseconds after that, is called the period of contraction. This is when those filaments are actively pulling on each other. The muscle is actively shortening. Once it has shortened to its amount that it's going to based on that stimulus it received, then the period of relaxation occurs. That's when the calcium is being reabsorbed by the SR, the thick and thin filaments are letting go of each other, and then forces opposing that muscle contraction might start pulling the muscle back out again. And we see in this case that most of the time in this experience, from 0 to 140 milliseconds, was involved in the relaxation period. So contraction pretty quick, relaxation may take a little bit longer to carry out. But that's a generic muscle contraction. If we look at specifics in the lower image here, we'll discover that different muscles have different rates of muscle contraction based on what it is they're supposed to do. All of them have that approximately 5 millisecond latent period, but then how quickly they finish their period of contraction and how quickly they go through their period of relaxation will differ. Our first muscle here with the dark blue line, an extraocular muscle. This is a muscle that actually helps to move the eye within the eye socket. And would you then expect that eyes need to move fairly quickly to keep track of moving objects and to keep track of your environment? The answer is yes, it needs to contract quickly to quickly move the eye. So we are not surprised when we see the entire process, from start to finish, only taking about 20 milliseconds. Compared to our generic muscle in the upper image, it took more than 20 milliseconds to reach our full contraction and another 120 after that to reach relaxation. So this one very quickly contracts, very quickly relaxes. The gastrocnemius is the calf muscle, and you can see here that it's still much faster than our generic muscle at the top, but much slower than the eye muscle, so its start to finish time is around 75 milliseconds. The third muscle here, the soleus, is also found in the back leg, or the posterior portion of the leg, and its total time here runs out to 200 milliseconds. So the gastrocnemius is the calf muscle on the outside, and right underneath it we find the soleus, and both of them are going to be involved to some degree in walking, running, jumping, all those things that the lower leg gives us. But ask yourself this. Which one of these is going to be more significantly involved in jumping, and which one is going to be more significantly involved in walking? Which of those two options requires a faster muscle contraction? To jump requires a faster muscle contraction because it has to actually contract so quickly that it launches you off the ground. That means the gastrocnemius is more of the jumping muscle. Soleus is a greater contributor to walking than it is to jumping because it takes longer to get its job done, and that's just not suited for jumping. Gastrocnemius would also be involved in walking, but it's going to be a more significant player in jumping, and the soleus would have more of a significant contribution in walking. So what the muscle needs to accomplish is going to determine how long it takes to contract. What we were looking at there is a single stimulus, which would result perhaps in a single muscle twitch. So that entire process we just looked at here, from latent period, contraction, relaxation, all of that together is called a muscle twitch. So if we look here at a single stimulus gives us a single muscle twitch, that then means there's a maximum amount of force that a single muscle twitch or a single muscle contraction can give us. So if we look at figure A here, we have the stimulus, we get our contraction, we get relaxation, and that takes however long it takes. There was that maximum level of force it could generate with a single stimulus, with a single nerve signal. What happens, though, if we give it another stimulus? So let's go over here to B. We give it our original stimulus, it generates that force. It starts to enter relaxation. But what if we give it another stimulus before it completes relaxation? Look what happens. We get a contraction generating a certain amount of force, starts to relax again. But we actually, at the second contraction, generated more force than we could have with the first because we started at a different starting point. We started before the muscle was completely relaxed, so it generated roughly the same amount of force with the second contraction as it did with the first, but it started at a higher place, so it ended at a higher place. If we hit it with another stimulus again before that second one relaxed, and we kept hitting it, we would keep building that force generated until we reached the maximum that it could possibly generate for that muscle's capabilities. At that point, that would be considered tetanus. Tetanus is muscle contraction at its perhaps maximum. So incomplete tetanus means we're working towards the maximum contraction. We haven't quite maxed it out yet, and we're entering some degree of relaxation between stimulus events. In this case, tetanus doesn't mean lockjaw. It doesn't mean an infection with Clostridium tetani, although significant muscle contraction, unreversible muscle contraction does occur with that particular problem. So that's where that came from, is what we call down here in figure C, fused or complete tetanus. That's what you would experience as a symptom of a tetanus infection. So with this figure C, what we see is stimuli that are so close together that we don't have a chance for that muscle to enter a period of relaxation at all. So it's achieving very quickly its maximum contraction force, and it is maintaining that contraction force for that period of time. So we hit it, up to that maximum the muscle could ever produce. The more stimulus we give it, the more generation of force we achieve. Now there is going to be a period of relaxation no matter what you do with the frequency of stimulus. So let's say we continue hitting it with that stimulus over and over again, but at some point the muscle will enter a period of muscle fatigue. And at that point, you've used the available energy. The muscle cell cannot maintain that activity anymore. In other words, it needs a break to regenerate its energy and to get rid of some of the lactic acid perhaps that's building up. And at that point, the muscle will enter a period of relaxation. So if you've been trying, let's say, to hold something, and let's just do that for a moment. If you have your textbook with you, go ahead and grab hold of that textbook with one hand and hold it out to your side at full arm's length. So you're trying to hold it out to the side with your arms straight out. So at first you can do that because you've achieved tetanus. You've got the muscles generating that force. But after a little bit of time, some of you perhaps already are starting to feel that book shake a little bit. You're starting to feel your muscles tremor and shake, and your shoulder starts to shake, and you might start having a little bit of a burning sensation occurring. And that is your muscles reaching their fatigue point. The book weighs a couple pounds, so that reaches your fatigue point, typically for the average person, relatively quickly. But what you discover is the farther out you hold the book from the body, the harder it is to hold it up. And that's physics that we don't have time to get into today, but the farther out the force is generated on an object, the less force there is. So you're reaching muscle fatigue. You're feeling the shaking of the muscles. And what's happening is the muscle is starting to relax, but that stimulus that's still being applied basically slaps it and says, no, get back up there and contract again. So the contracting and relaxing very quickly starts to give you those muscles shaking. And that might go for a certain period of time before the book just drops and you can't hold it up any longer. I'll show you a little snip of a video here in a little bit of very obvious body-wide muscle fatigue and failure. And you'll also see what some individuals are capable of with muscles. And we'll get to that in a little bit here. So there was that single twitch that we saw giving that outcome. There was building up, accumulating more and more force generated with the multiple stimuli a little bit slowly. And there's the fused complete tetanus so that at the end you'll get muscle fatigue and failure. So let's look at that from a different perspective. We get a particular stimulus from a nerve, let's say stimulus 1, and it has a certain voltage to it. Remember we saw that about the 30 millivolt voltage was when we got an actual muscle contraction to occur. So there is this idea of a threshold stimulus, a minimum voltage that must be generated for the muscle to actually contract. And anything below the threshold doesn't give you any kind of contraction. And the farther above that threshold you go, in theory, gives you a stronger contraction. So this means not only does increased frequency of stimulation give us more force, but increased intensity of stimulation generates more force. So stimulus 1 wasn't enough. And then we look here at the number of motor units that actually contracted, nothing. And down here, no force generated. Stimulus 2 didn't meet the threshold, nothing contracting, no force generated. Stimulus 3 met the threshold, some of the functional units contracted, and some force was generated. But you can see here, the higher the stimulus goes, the more of those individual sliding filament sets get engaged, and the more force we generate, up to a maximal stimulus. Just like we saw with the complete tetanus. We generated as much force as we possibly could, and if we gave it faster stimuli, it didn't increase the force generated. And also here we'll see if we increase the voltage of the stimulus past the maximum, we've already engaged all of the muscle fibers available, we've already generated the maximum force that's possible, and we're not going to get anything past that. Another idea of what will give us more force is what size of muscle fiber or cell did we use. They come in small, medium, and large. So if you start out trying to pick up a pencil, what you're actually going to do is you're going to use a few small muscle fibers and try to see if you're able to do that job. If the signal comes back to the brain saying, we didn't achieve what you wanted, the brain says, fine, try more. So it might recruit more small muscle fibers. In the case of picking up a pencil, you don't notice that recruitment process of building force until you finally move something because it was a small object. Let's say you were to try to pick up a much larger object, and let's say it weighed a little bit more than you predicted that it would when you started to pick it up. You might then notice that your first attempt didn't work so well. So you would then consciously put more force into it, and that's just this idea of recruiting more and more muscles to the cause until you get that threshold stimulus, until you get enough of them engaged, in that case to move whatever it was you were trying to move. So you can increase force by going from a small to a medium fiber, or you can even go to a large fiber. So the larger the fiber you use, the more force you can generate that way. This also applies to the idea of muscle building. If you start out with small muscle fibers and you're trying to build muscle, you're not actually making new muscle cells. You're simply taking muscle cells that are there and you're increasing their size. So you can perhaps turn small fibers into medium, medium fibers into large, and within reason, the larger you make the fiber, the more force it's capable of generating. Obviously, there's a maximum point there at which there's no longer any value to that process, and we'll see that here in a few minutes as well with one of those videos. Here's the idea of an isotonic contraction. Sometimes you might hear it referred to as a concentric contraction. What happens is, in this case, if there's a 3 kilogram resistance that the muscle is trying to move, as long as that muscle produces at least 3 kilograms of force, it will move that object. So an isotonic contraction results in the muscle shortening. And what you see here is that the muscle was a particular length. So down here we've got our length of whatever it was. As it contracts and generates force, you can see here the length gets shorter and shorter, and we're seeing it here shortening. So remember, those filaments were sliding towards each other, shortening themselves, because they were attached to filaments on both sides, and in this case perhaps those filaments were also contracting. The overall muscle gets shorter. It also gets bigger around. And this is the idea of flexing your muscles. Flexing your muscles is an isotonic contraction. It moves part of your body that it's attached to. So if you look at people doing a muscle builder pose, they flex at the elbow, which allows the biceps muscle to shorten to its maximum degree. They're going to flex at the knees and flex and twist at the hips, allowing muscles more opportunity to shorten. And the shorter the muscle gets, the more bulged it gets. If you're looking for maximum muscle bulge, you need to allow for maximum muscle shortening. In an isometric contraction, what happens is the muscle is not capable of generating enough force to move whatever it's attached to. Because it's not allowed to shorten, it doesn't really change in length, and it doesn't really change in diameter. So we see here at the bottom, we look at the force generated was, in this case, let's say, just a little over 5 kilograms. We needed 6, so nothing moved. That means the length of the muscle here didn't change. So this would be what happened if you tried to move something that didn't actually move. Or if you place your palms firmly on the table, keep your arms locked straight, and attempt to flex your muscles of your arm, you're not going to see significant bulging of the biceps because they're not really allowed to shorten. You might see a very minimal amount of bulging, but nothing compared to what would happen if you actually allowed the arm to move at the elbow. Muscles require energy. And I'm not going to belabor this point, but there are 3 different ways that muscles can go about generating energy. The first one here is direct phosphorylation. That involves creatine, and you've perhaps heard of creatine before in the world of muscle building and muscle performance and that sort of thing. And what they're doing is they're trying to give the muscle a huge batch of this creatine energy source so that they can get a significant amount of energy released and produced. But you see here the duration is only in the matter of seconds, so 15 seconds or less. So this is bursts of energy, not necessarily prolonged energy source. The anaerobic pathway is going to involve producing energy without using oxygen. This is going to produce a little bit of energy, but not a whole lot really compared to what you could have gotten from that sugar. It's also going to produce lactic acid as a side effect. If that lactic acid level builds up too much, it causes muscle cramps. So most muscle cramps are a result of excess lactic acid production during anaerobic respiration. The duration of that energy lasts for up to a minute, let's say, but really less than that probably. So this is a limited energy source as well. Really, the aerobic pathway is the most effective pathway, because you get the most possible energy out of that molecule of sugar in the first place. It takes a little bit longer to produce, but also provides energy in the range of hours, not seconds. So this is perhaps the long-term better option for energy production if at all possible. And there are no negative side effects of lactic acid and causing cramps and that sort of thing. So here's a different way of looking at that. Energy already present in muscles is going to be used in the first few seconds. A few seconds into that activity, the available energy is used. So here around the 10-second mark, we have to switch to that creatine source. Then we're going to do the anaerobic activity for a couple of seconds up to a minute here, creating energy in that anaerobic respiration. So if your activity lasted less than a minute, you had the first few seconds was already present energy, the next few seconds was creatine sourced energy, and then the rest of that minute was anaerobic respiration. If you're going to do the hours thing, you need to go the aerobic pathway because, again, this other stuff only lasts for up to about a minute or so. Now, it can be very powerful and very intense production of energy, but again, very, very time limited. Sprinting versus long distance running, perhaps we could say. So to get more muscle force generated, we've already talked about use more of the muscle fibers that are available, use larger muscle fibers, increase the frequency of stimulation and the intensity of stimulation. And here's one we haven't talked about yet. Have the appropriate amount of stretch present in that muscle. So let's look at the optimal stretch range. What we have here is the percentage of resting length of that contractile unit. So up here at the first, we have those units contracted. They're as short as they can get. So that's less than 100% of their resting length. Here's our resting length, so they're not contracted, they're just relaxed but not stretched. And then over here we have stretched. So they're beyond resting. They're literally about to fall apart from each other here. So what we discover is that the optimum operating length is between 80 and 120% of the resting length. So a little bit shorter than resting length, a little bit stretched past resting length, but really somewhere in the middle. You see less force generated down here because there's less place for the thick and thin filaments to slide back and forth. So you've already done most all that muscle is capable of doing. Out here on the stretched end of things, the thick and thin filaments are barely hanging on to each other. And you can't generate a lot of force when you're barely attached. Think about extending your arms fully out to the sides. Grab hold of something on both sides that's relatively heavy and try to move it towards the middle together. You'll find while the arms are fully extended, you're not capable of generating great amounts of force. As those objects start to get closer together and your arms start getting a little closer to shoulder width from each other, then you start to feel more power because you're entering that 80 to 100% range. Then as you get closer together in the middle, you literally start running out of space for contraction. The arms start bumping into the body. There's just nowhere left to go with that, and you start seeing a generation of force go down a little bit. So it has to do with how much farther can you go and at what kind of grip does the thick and thin filament have on each other. Let's talk for a moment about fast twitch and slow twitch muscles. They are just like they sound. Slow twitch muscles contract more slowly. Fast twitch muscles contract more rapidly. And if you remember the comparison between the eye muscle and the soleus, a much slower contracting muscle, you're starting to get the idea of fast versus slow. Still fast because it completes in under a second, but comparative to other muscles can be quite slow. What I really want to talk about here is the different ways that these fast and slow twitch muscles get their energy and work. Slow twitch muscles, or what is labeled here as slow oxidative fibers, are going to get their energy from aerobic respiration. Fast oxidative fibers are going to get some from aerobic and some from anaerobic. The fast glycolytic will get all of theirs from anaerobic. So really, slow twitch is aerobic. Fast twitch, to some degree, gets its energy from anaerobic. Remember, that was the stuff that could be done in a few seconds, but only lasted for a few seconds as well. Everyone has both slow twitch and fast twitch muscles throughout the body. The difference in how much slow twitch you have relative to how much fast twitch you have determines whether you're a better long distance runner or a better sprinter. So if you're better at sprinting than you are at running long distance, that means you have more fast twitch fibers than you have slow twitch fibers. If you're more of a long distance runner and you're not very fast, you have more slow twitch fibers and fewer fast twitch fibers. I remember in junior high, I was on the track team, and not because I was gifted in running and in track and field events, mostly because I wanted to get out of class, and that was good for getting out of class for an entire day multiple times per year. At that point in life, that sounded like a pretty good deal. The coach would put me in the 100-meter sprints and in the 100-meter hurdles. I was not super fast, so I wasn't biologically suited to be a sprinter because it turns out that I have more slow twitch fibers than I have fast twitch fibers. I was competing against an individual from another school on a regular basis that had far more fast twitch than slow twitch fibers. And he would run the 100-meter sprint in about 3 seconds less than I would. So I was 3 seconds slower, which doesn't sound like that big a deal, but in the world of a 100-meter sprint, that's a long distance. So his fast twitch muscle fibers could contract very rapidly, moving his body very rapidly. And this is really impressive. In 8th grade, he was about a second to a second and a half away from instant Olympic qualifying time in the 100-meter sprint. If he had been willing to train his fast twitch muscles to maximize their performance abilities, he could have qualified for the Olympics in 8th grade. He wouldn't have won at the Olympic level, but he could have gone, and that would have been very, very impressive. In the 200-meter sprint, he would actually run a faster time per 100 meters than he did in the 100 because he had a little bit more time to get wound up and going, and so that high speed that he was able to achieve was in play for a longer period of time. Beyond 200 meters, though, he was relatively useless. So if we were to get to, let's say, a half-mile event, I would have been able to defeat him no problem because his fast-twitch fibers using anaerobic respiration would have very quickly built up lactic acid and caused problems. My slow-twitch fibers doing more of an aerobic respiration route would have been able to perform for a longer period of time. So in short sprints, there was no way in the world I could beat him. In a longer distance, even though I never trained to become good at that either, there was no way he could have beaten me because his muscles weren't biologically capable of prolonged performance. We've been talking about skeletal muscle here. There's also cardiac muscle and smooth muscle. So this is a little bit of a comparison between what they look like and how they function. Take a look at that table. It's good stuff. Does this individual exhibit adequate muscle mass for the arms? And we're going to assume the rest of the body is shaped similarly to this. Most of you are probably saying that's at least adequate, and some of you are perhaps saying it's excessive amounts of muscle mass. So this gets us to the idea of muscle builders and some of the things that they do trying to achieve greater muscle mass. Let's talk briefly about steroid use. This kind of muscle mass you see here would probably be possible just by working out more at the gym. The more you use a muscle and the greater force you apply to the muscle, within reason, the larger the muscle fibers become. To go much past this, though, you're going to need the use of steroids. And here in a little bit, we'll take a look at some individuals clearly using steroids and a number of other enhancement compounds. Basically, steroids artificially mimic testosterone. So testosterone is normally produced in the body, and this is why males usually have more muscle mass than females. It's because typically a male has higher testosterone levels. Natural testosterone has a maximum level at which, if you increase the levels of testosterone, you do not get a corresponding increase in muscle mass. Anabolic steroids, so synthetic steroids, don't have a maximum threshold. So in theory, the more testosterone, the more artificial testosterone you dump into the system, the more muscle mass you get. Now that can lead to the point of things like biceps exploding, and so too much muscle mass can be a real problem, to the point that you can't move well, it doesn't look good, it just looks like a problem. Another issue with anabolic steroids is that it turns off the body's natural steroid production processes. The body basically looks and says, we're getting all this testosterone for free, why are we making our own? Which then means the natural effects of testosterone in the rest of the body start to go away. So testosterone was maintaining hair on the head. And you'll see with a lot of these bodybuilders, the hair on top of their head gets a little thin. The testosterone was producing and maintaining voice, so a male voice might become more feminized in a male abusing anabolic steroids. Reproductive genitalia was driven by testosterone, but too much anabolic testosterone gives you reduction in external genitalia size. Muscles actually become brittle over time. Liver, kidney, and other organs like that fail prematurely. And you get an abnormal psychological condition known as roid rage, in which you engage in abnormally aggressive and overly problematic behavior. So let's go take a look here just for a moment at some individuals who have taken this muscle thing perhaps a little far. What we see here are some pictures of Jay Cutler, and not Jay Cutler the athlete, but Jay Cutler the Mr. Olympia contestant. And we can see here, let's just look at this one. We can see here the amount of muscle mass and definition present. So would you consider this amount of muscle mass to be excessive? To be in the way? And you can see here blood vessels popping out. the size of pencils outside the skin. They're not supposed to do that. And so it kind of looks like he's a little bit in pain there. If we look at, let's go with this right here perhaps. This sort of definition, you notice the arms are bent a little bit at the elbows. The shoulders are flexed a little bit. The torso is twisted. The knees are bent a little bit. All of those to allow that maximum muscle contraction to occur. If we look at this image here, we can see a little bit of thinning hair. From that, sometimes in these competitions that are basically built on who has the most beautiful flex, who has the most significant degree of muscle contraction visible, and it's quite subjective one time to the next. Here we have Ronnie Coleman and Jay Cutler, and they were competitors for many years. And you can see they're both very, very muscular individuals. But in one event, Mr. Cutler won, Mr. Coleman lost, and Mr. Coleman was actually backstage bawling his eyes out like a baby because he didn't happen to flex just right to impress the judges most significantly to win that particular event. If you were to look at them long term, besides the problems we've talked about so far, what happens to someone who has done that to their body and then later cannot really keep it up? I think we can say this individual right here is not necessarily at his prime. Again, these guys are working really hard to keep that shape, but it's starting to decline. So no matter what you do, muscle performance and size and mass and everything like that over time is going to decline to some degree. So that didn't look that great, although it could be a lot worse, I suppose. So ladies, ask yourself this. Do these bodybuilder individuals, whether they're old, young, or in the middle, look good? The average person says it doesn't look good. So why are these individuals doing it, clearly thinking they look good, if they don't really look good? And I suppose that just comes down to a matter of opinion and perspective. There are actually some psychological conditions associated with this called muscular dysmorphia, when you look at yourself in the mirror and you're never convinced that you're muscular enough. So a lot of these individuals perhaps might be suffering from that psychological condition. But most females will say that male bodybuilders do not look good. Let's look at it from the other perspective, and if there are any guys in the audience here, let's ask yourself, does this look good? Does that look good? And I'm guessing most guys are saying absolutely not. That does not look good at all to me. And there's a couple of reasons for that. Take a look at that one perhaps. No, that's still a little bit scary too. So a couple of problems there. And one is that we just personally wouldn't necessarily find it so attractive. But two, we have this psychological idea that, well, the female might actually be able to beat us up. And we have a kind of a real psychological hang-up with that as well. Again, failing to reach the definition of attractiveness here, perhaps. To be completely balanced, let's look at what happens as age progresses here. And we discover that it didn't really age so well either. And she looks like she's in a little bit of pain as well. So what you may have as a younger person, you're probably not going to be able to keep as you get older. It certainly is going to be more work anyway. So I would propose that this sort of level of taking bodybuilding to is something that biologically, cosmetically, and every other way you can imagine, perhaps is not the best of ideas. What we're going to look at here are some individuals who are very much working on actual performance strength of their muscles. So when you look at these individuals, they don't necessarily look carved and sculpted like the Jay Cutlers and the Ronnie Colemans did, but they are capable of producing tremendous amounts of force. And what we see here is the challenge is to pick up this rock, and this rock weighs over 400 pounds, by the way. The objective is to pick up the rock, stand up with it, and place it on their shoulder in a controlled format. A number of different contestants are going to be involved in this. So let's just go ahead and take a look at the first contestant. He's going to try to pick up the rock, and picking up the rock is enough of a challenge, and most all the competitors can do that. The challenge then becomes, though, getting it up to the shoulder. So let's give him a second here. So that was the easy part, getting it up to the knees. Then maintain the grip to get it on up to the shoulder is a challenge. I'll just go ahead and spare you the time here. This individual is not capable of doing that. So we'll jump up to another competitor here. Let's go to this one. This guy's 6'5", weighs 330 pounds, so he's a mountain of a man, 24 years old at this point, and let's see what he's able to do with it. His picking up technique was a little bit different there, using more of his back. He sort of made that look easy. Now the objective of this particular competition was to shoulder the stone as many times as you possibly could. So in the interest of time, I'll just go ahead and tell you that he was able to shoulder the stone multiple times, and every time for the most part made it look pretty easy. Let's look at another individual here. And this individual is going to try to do again the same thing. But what we're going to see with him is he's going to experience full body muscle fatigue and failure. And when that happens, it will be very obvious as to what's going on there. So let's let him go ahead and try to get it picked up. Notice his whole body starts to shake there, and he wasn't able to quite hold it up very well there. Let's back it up a little bit because it looks like we missed the best part of the body shaking there. So you started to shake there a little bit, just getting it up to the knees. There we go. Full body shaking top to bottom there. Clearly he was under a great deal of strain at that point. In a later competition, there was actually so much pressure on his body trying to lift something that he actually had blood spray out of his nose. So this sort of thing, often in these events, can lead to things like prolapsed rectum, development of hernias, and other issues right on the spot. And part of the reason of that belt that they all have around their waist is to keep their abdominal cavity from exploding with the pressure. So it does some pretty ugly things to the body in that process. Other individuals were more or less capable of picking up, and some of them getting to the shoulders and some of them not getting to the shoulders. But the individual we saw there pick it up successfully the first time was by far the winner. He was able to pick it up 5 times to his shoulder. All the rest never came anywhere close to that. Some other performance impressiveness, I guess we should say, is, let's say this one right here. All kinds of different ways that they have developed to try to see who can really move something the biggest or is the strongest. And this particular collection of wooden timbers here is quite heavy, and the objective is to pick it up and carry it up this sloped ramp to the top. So not only pick it up, but carry it and carry it up a hill. That becomes even more difficult. So let's take a quick look at that attempt. With these events, there's a lot of talking and not so much actual doing. So here's an attempt to do. And this individual is one of the shorter ones in the competition. So some of these events actually being taller is an advantage. These shorter folks are going to have to pick it up higher relative to their body size to be able to clear it off the ground and actually carry it. So sometimes vertical height attainment is an advantage here. So let's see if this individual can do it. Clearly straining pressure, has to stop along the way and get a new grip and take off. That was a 900-pound set of timbers there, so that's a significant chore for anyone. He ran out of time and got it halfway there. Far better than I would have been able to do, of course, but in the grand scheme of things, not that wonderful. Let's take a look at the person who won the stone lifting and see how he does with carrying timbers. Got most of the way with it. He didn't dominate this particular competition quite as much as he did the first, but still significant, impressive performance. What about carrying a car? Would that be something that would be a little more difficult to do? And again, let's look at the same individual that we've just seen here doing pretty well across the events. So let's get to the point here where we're actually going to pick up the car. So he's picked up the car, carrying the car, and has got it across the finish line. And that particular performance was good for a world record for that particular thing. Now, obviously, they've removed the glass, they've removed the engine transmission, but there's still plenty of weight there. So that's still a significant amount of weight to pick up and carry. So very impressive to be able to do that. And again, those guys aren't necessarily looking like they're so incredibly sculpted like the Cutlers and such were, but very impressive nonetheless. So that is the sort of thing that muscle performance can theoretically do for someone. There's going to be a lot of work in that process as well. And if you want to watch that sort of thing, just do a YouTube search for Arnold Challenge, and you'll find lots and lots of different events that they go through, all of them crazy complicated to be able to do. Let's cap this performance here off with the idea of, okay, carrying a car was impressive. What if we instead pull an airplane? This is bigger than a car. And here we're going to try to pull this very large airplane. The trick is going to be getting it started. And once you get an object moving, it's a lot easier to keep it moving than it is to get it started in the first place. So it will take each of these competitors a little bit to get it going. Again, this is not a little airplane. This is a military transport aircraft. So he's got it going there. The objective is to get it to cross the line there. He's going pretty good. And he managed to get it to cross the line. Another competitor there. Lots of these guys were able to get it going some places, but the further they went, the muscles start to fatigue. So the trick here was to generate muscle force, but not have to experience muscle fatigue, and that's probably the challenge with this. So anyway, just some examples of muscle performance and what it's capable of within reason. The average person wouldn't need to be able to do this, but anyway, there you have it. Hopefully this was enjoyable, informative, and you learned a lot. See you next time.